Hi, in this lecture, we will talk about linear and nonlinear solvers. Linear and nonlinear solvers are very important in finite element when we solve AX equal B, which is often the last step in many different forms of numerical methods. I'm going to start with a little bit mathematical preliminaries, and then we'll talk about linear and nonlinear solvers. So we'll need to know the concept of a matrix norm. We've already learned about a vector norm. So the way a matrix norm is defined is that we use our definition of a vector norm and we solve this optimization problem. So maximizing over non-zero vectors x, the vector norm of AX divided by normalized by the norm of x. And then P could be any number depending on you're doing an L2 norm, L1 norm, or whatever norm you're calculating. So this is the definition of an induced matrix norm. So for example, the L2 norm, if P is equal to 2, that's the Euclidean norm, which is square root of the largest eigenvalue of A transpose A. The Frobenius norm, the other popular norm, is a square root of sum of eigenvalues of A transpose A. Okay, so this norm, again, similar to vectors for matrices, you can think about it as some sort of metric for measuring how big that matrix operator is. Now, the other concept we need to distinguish here is the concept of conditioning versus stability, which comes up often in numerical methods. So conditioning is related to a given problem. So if a problem is not well conditioned, it has to do with the problem itself, nothing to do with our way of approaching the problem. But stability is different. Stability is related to our numerical algorithm that we choose. So if we have stability issues, by coming up with a different numerical algorithm, we may be able to improve it or resolve the issue. But if we have conditioning issue, that's not related to our algorithm, but that's rather the given problem. That's a difficult problem for us to solve. So we have to, think about it differently. So now let's take a look at this by defining this problem. So if you have a problem F that takes some input x, gives you some output y. If you perturb the inputs, so for inputs you have x plus delta x, you expect the outputs to also be perturbed by some delta y. Now, if you take delta x to be small, so this could be some numerical perturbations like round off errors or something to the input. If you take this delta x to be small, you expect the output, hopefully the delta y, the output to also be small. So if delta y is small, that's a well-conditioned problem. That has nothing to do with our algorithm that we're solving this problem, but that's rather the given problem F itself, the mapping itself in this case. If delta y is large, we call this problem an ill-conditioned problem. And we can measure it using this so-called condition number. So this is the definition of a condition number, this limit. When we perturb by some delta x, take the perturbation, go to 0. If you calculate how the output changes, normalized, and how the output relatively changes, and then normalize that by relative change in the input, we call that the condition number. And we hope for that to be small. The smaller the condition number, the easier it is to solve a problem. And we're going to see that how this gets translated to matrices and linear solver in a second. Okay, so now let's talk about linear solvers. In finite element, everything at the end of the day comes down to solving AX equal B. So for any problem, at the end of the day, we have to solve a linear system of equations where we know at the matrix A, we know the right-hand side vector B, and we want to solve this vector X, which is our degrees of freedom, the nodal solutions that we're trying to find. Now, analytically, at least you can write the answer to this linear system of equations as x equals A inverse B. We often talk about inverting a matrix, how easy it is to invert a matrix when we talk about linear solvers, but we really never, ever explicitly calculate A inverse. It's a very difficult and not practical problem to do. So we really directly find A inverse B using our AX equal B solvers without actually explicitly calculating the inverse. Now, how easy for this problem is depends on the condition number of the matrix A, which is, in this context of the AX equal B problem, it characterizes the sensitivity of our solution X with respect to perturbations on the inputs to this problem, which is the known B vector and the A matrix. And it tells us how easy it is to solve this linear system of equations. So the condition number could be used which is this given by this formula. So if you know the matrix A, we can calculate the condition number. Now, for most problems that are diagonalizable, so for normal matrices, this is basically nothing but the absolute value of the largest eigenvalue divided by the smallest eigenvalue. So essentially, if you know the spectrum, the range of eigenvalues you have, the largest eigenvalue divided by the smallest eigenvalue, that's your condition number. And you want this to be small. So the cases that the problems become challenging to solve, the linear solvers become challenging to solve, is when your largest eigenvalue is orders of magnitude different from your smallest eigenvalue. And this happens when the problem that you're solving has disparate, very, very different features. And in practice, in finite element, these ill-conditioned matrices, which makes it difficult for us to solve problems, they appear in two cases usually. One is when you have very different physics, disparate physics. So for example, you're solving a solid mechanics problem and you have wide variations in stiffness. So one part of your geometry is very stiff, the other part is not so stiff. There are orders of magnitude difference between them. That leads itself to large condition numbers. So really, and the reason is that, this comes down to the stiffness matrix, right? And its eigenvalues of the stiffness matrix, they're closely related to the physics of the problem that you're trying to solve. So the large spectrum between the eigenvalues of the matrix represents that your physics has large scale variations between the different scales and the physics of the problem. Okay, so that's one example of disparate physics. So you have very, very dramatic variations in the physics that you're trying to solve. The other case scenario where you can get ill-conditioned matrices in finite element is that if you have disparate mesh edge sizes. So you have somewhere in your mesh very, very small elements, and somewhere you have much larger elements. If the difference between that very small and large elements are huge, that can also cause ill conditioning. So now to solve AX equal B, we have two classes of approaches that we can take. We have direct solvers and we have iterative solvers. So direct solvers are, they're direct, they don't iterate, so there's no tolerance. So they're really good, but the problem is that they only work for small to maybe moderate size problems. So if you have a small scale problem or even a moderate problem, depending on how much memory you have, the direct solvers are the best choice. But if you have large problems, which are often the case in many practical FEM problems, like CFD problems, then you need to use iterative solvers. So for direct solvers, the most popular method is Gaussian elimination or LU decomposition. So essentially, we take a matrix A, we perform Gaussian elimination on it to decompose it into multiplication of two matrices, L and U. L is a lower trigonal matrix, so all zeros above the diagonal, and U is an upper trigonal matrix, so all zeros below the diagonal. So by Gaussian elimination, we can find these two matrices L and U. And once you find them, if you plug that in for our AX equal B problem, this is what we get. And we can now easily solve this problem by two steps. First, we call UX to be Y. Okay, so we call this whole thing Y. And then we solve for L times Y equal B. So first, we go ahead and solve this one. So B we know, that's the right-hand side vector. L and U we also know. So this is a linear system that I can solve. And this is actually pretty easy to solve because L is lower trigonal. So I essentially just first find Y1, very trivial, just one equation here. Then I find Y2 here and keep going. So it's just a simple forward substitution to solve for Y. Once I find Y, now I know what U times X is equal to. So U times X is equal to Y. I have already found Y. And U is an upper trigonal matrix. So that's also trivial to find all the X's. You just start from the end now, back substitution, and you solve first xn minus 1, and you find all of them all the way to the first unknown X. So now the beautiful thing about direct solvers, in my opinion, for finite element or CFD modeling is that once you find this L and U matrix, once you do the decomposition, which is the expensive and more time-consuming step, then you can use them for any right-hand side B to solve AX equal B. You don't have to recalculate them. You just store them once, you calculate, find them once, and then you solve AX equal B pretty fast using just these forward and backward substitutions for any right-hand side vector B. So that basically makes it pretty easy. And the practically you can think of that as when your stiffness matrix is remaining the same. It's just that your source term your B is changing. For example, you're iteratively solving a problem for different source terms, right? In that case, your stiffness matrix, your matrix A will be the same. You just want to change the right-hand side. Or maybe you're changing the Newman boundary conditions or the Dirichlet boundary condition values, as long as their location is the same, then you're only changing the B matrix. So A is still remaining the same. So you can quickly solve for these different variations in your problem in those specific cases. And only do the expensive AX equal B solve just once, and then quickly do the back substitution. Okay, now for the next class of problems are iterative solvers, and they're essential once the problem is large. Once the matrix A is large, then we can't use direct methods because they're really memory intensive, and they're also computationally expensive too. So we need to use iterative methods, and we have to keep in mind that direct methods are exact. Of course, there's round-off error, but they're exact methods. But iterative methods are an approximation. They approximate and iteratively approximate the solution. So some popular methods are GMRes, biconjugate SAP, conjugate gradient. And in FEniCS, you can determine the type of linear solver you want to use. You can choose what type of iterative solver you want to use. You can just call them. Or if you're using direct solver, you can call what type of direct solver you want to use. From my experience, GMRes is probably one of the more popular iterative methods. But from my experience for advection-dominated problems, so specifically when we do advection diffusion equation and very high Pector number regimes that can cause some stability problems, the biconjugate STAB method usually gives better results in those cases. But in a lot of problems, GMRes is a good choice for iterative methods. So in iteratively, we solve the problem iteratively until we satisfy a pre-specified residual, for example, 10 to the power minus 10, right? So we have to iterate until we reach that tolerance. So now for large condition numbers, these iterations might be very slow. We might need many hundreds of thousands of iterations to reach reasonable tolerance. So one solution to this issue is to use preconditioners to reduce the condition number. And from my experience, whenever you're using iterative solvers for difficult problems, practical CFD problems, most often the preconditioners are absolutely essential to use. They just give you tremendous speed up. So and the way that the concept is that if you're solving X equal P, you can multiply both sides by a matrix P inverse. Okay, and you can choose this matrix P. So you're allowed to do that. You're allowed to multiply both sides by a matrix. And this matrix P, you should choose it such that P inverse A now has a smaller condition number compared to A. Because now this P inverse A is really playing the role of A. You have to solve for this matrix, right? So if this new matrix now has a lower condition number, now you're good. You can do your X equal B faster. Okay. And again, in FEniCS, you can have access to choosing different preconditioner numbers, different preconditioners depending on what iterative method you select. Okay, so finally, we have the concept of nonlinear solvers. So in Navier-Stokes, the advection term is nonlinear, and in the coupled UP approach, we need to deal with it, the nonlinear problem. In the fractional steps method, you saw that we could, get away with that by evaluating that term from the previous time step. Now, here, the most popular method to do nonlinear solvers is the Newton method, where you basically, I'm going to explain it in a moment, but the important thing for Newton method is that your initial guess must be close to the solution. Otherwise, it will not converge. If you're close enough to the solution, Newton method is awesome. It converges pretty fast. It's second order. So for example, in a typical CFD simulation with the UP approach, maybe you need 3 or 4 Newton iterations. It converges really fast. But you need to make sure that your initial guess is close enough to the solution. And that in the unsteady Navier-Stokes equation problem, you can take care of that by making sure that your time step is smaller. Now, how does Newton work? So this is a quick review of how Newton works. Let's say you want to solve f of x equals 0, where this is a nonlinear scalar equation. This is the iterative formula for finding the solution x. So you have to calculate the derivative of f prime. You start with some initial guess, and you keep iterating until you reach some tolerance. In the case where we have systems of equations, we deal with these vector equations. So in this case, we have to calculate the Jacobian of f. So the Jacobian will kind of represent f prime, and the inverse of the Jacobian will be equivalent to 1 over f prime here. So f is a vector, so its Jacobian, or really the gradient of f, is a matrix. Okay, so now this becomes your iteration formula. Now, as I mentioned, we never really like to explicitly calculate the inverse, so you can take this equation and reform, take J inverse to the other side. So if you do that, now you don't have really the inverse anymore, but now you have an AX equal B to solve. So this is like your A matrix, this is your unknown X, and the rest are the right-hand side. So this becomes now like an AX equal B linear system of equation that you have to solve, and then you iterate for convergence. And based on a pre-specified tolerance or total number of iterations that you like to have for your nonlinear solve.